Good morning, everyone, and welcome to this session of the CoE talk or weekly seminar. To those here and, of course, to those afar. We are honored today to have Professor Manfred Möller, who is well known, well, I suppose, throughout the country. He's been active in research, active in teaching, and all kinds of activities. Professor Möller actually is well known to, particularly to us, because he's still in the school as an emeritus professor, and welcome to the talk this week. I like the title of the talk, about pencils and so. So Professor Möller will give us more details on this talk.
Thank you very much, Abdul, for the introduction. Good morning to everyone, close and far. What I want to give here is a survey talk. So there are no brand new results. It's more about motivations and how to deal with operator pencils. And the title, okay, let me just show it again, is Quadratic operator pencils. That's just a particular case on which I will concentrate later on. So what is the main idea? The main idea here is that if you look at dynamic, or one of the approaches, one of the tasks in the background, if you look at dynamical problems in physics, then they are often governed by linear partial differential equations in space-time. So, and if we now do separation of variables, then a complex parameter omega occurs, and that gives rise to an operator depending then on a parameter, and this parameter is the eigenvalue parameters, or what's in particular important, then that operator is no longer, and the easiest case is A minus lambda identity, then that part, that operator is not invertible, then one gets solutions. And so that's at large the well-known motivation, or well-known motivation to consider spectral problem. Now, A minus lambda identity, in particular, when A is self-adjoint, is a very particular case, very important case. But in many cases, one cannot just simply, like for the wave equation, then one puts lambda equals omega squared, then one gets an operator of that form A minus lambda I. There are many problems where one cannot just have the parameter lambda linearly. And so let us look at, in general, a formal polynomial operator with L of lambda, which is also formed some k from 0 to L, lambda to the power k of times a to the k, where a to the k are certain linear operators. And that is just right mark here. And the case of self-adjoint operators, this A minus lambda identity is very special. It has very special properties of the spectrum a priori properties. One knows that the spectrum is real. One has orthogonality of the eigenspaces and so on. And now, what happens when we have not just A minus lambda identity, but as on the previous slide, that operator pencil operators dependent polynomial on lambda are also called operator pencils, which the name comes from. And yes, okay, we can then write the self-adjoint operator in the Hilbert space for A minus lambda identity. If we don't have self-adjointness, then, and that's one of the main ingredients of the approach I want to present here, then it's no longer necessary to have unbounded operators. Differential operators, which are self-adjoint, are unbounded, and in that case, one can actually take that operator as an operator from the Banner space E. The Banner space E is the domain of A equipped as a graph norm into the space, the original space F equal A. So that one can do easily with a single operator, and now we can apply the same principle to an operator polynomial L, actually for the operator polynomial L. Now, when all the AK are self-adjoint, okay, I'm swapping a little bit between self-adjoint and non-self-adjoint cases. As you see, to give different aspects, then we can take the domain of L as a domain or the intersection of the domains of all the individual operators in that tensor. But there are some challenges. Normally, we will, if you have self-adjoint operators, they are densely defined, but the intersection of those sets, subspaces, is no longer necessarily dense, so that's a challenge. And also, if we add up several operators with a parameter lambda, these operators then don't need to be closed anymore. Self-adjoint operators are closed by definition. And most importantly, if you take such as operator, tensor with self-adjoint operators, is there any meaning, any purpose to do that? Do they still have certain properties, particular properties of the spectrum? Now, another point here is that if you look at differential operators, then if you look at standard self-adjoint differential operator, so it has a differential operator and boundary conditions. These boundary conditions are normally considered to be homogeneous. So one requires the domain that the boundary conditions are satisfied. However, when the boundary conditions depend on lambda, on this parameter lambda, then that domain would normally change with lambda, which is not so good. So the idea then is to consider the boundary conditions inhomogeneously. That means in that at the bottom where T of lambda equals TD of lambda and TR of lambda. So the TD of lambda maps into F1 and is a boundary differential equation part of the operator, and the TR is a boundary part of the differential operator. I will give later some examples to explain how that works. And now I want to go one step further. It is not necessary for the abstract theory that T or L is just a polynomial. You can take any holomorphic operator. Then, and it's defined on a set omega, which is an open and connected set of the complex plane. So the lambda, that eigenvalue parameter, is a complex number. E and F are Banner spaces. Often they can be taken to be Hilbert spaces, but that's not important. And now T of lambda is bounded for all lambda in omega. Remember, I said before, using the graph norm, one can always for single operator, single closed operator, represented as a bounded operator. And holomorphic means that T has a local power series extension. And what we are mainly interested here is the spectrum of T. So the resultant set of T, row of T, is a set of lambda, where T of lambda is invertible. The resultant set is just a complement of, so the spectrum is a complement of the resultant set of this operator function T. And one advantage of that is, for example, if we assume that row of T is different from the empty set, so that there are at least some points in the resultant set, and that's again a reasonable assumption, then we can look at the inverse operator function on the resultant set of T, because then the operator is invertible, and that inverse operator function T with power -1 of lambda is again a holomorphic operator function. Now, then again, we want to look a little bit into the possibility of having self-adjoint tensors. Then for that we consider just polynomial tensors. Then we have that starting from our bounded tensor from E to F. And now F is split into F1 times F2 for our differential operator. Then we have that E into F1 is there. That's a reasonable assumption for our differential operator. Now assume that the boundary conditions are independent of lambda. That means the null space of T out from lambda is independent of lambda. And all the coefficients, AJ, now that would now be the restrictions of TK to the null space N. All of them are essentially adjoint. Then our tensor would be normally unbounded. The eigenvalues of T and lambda in any case will coincide. That means the null spaces also will coincide, the spectrum will coincide, and then we may use the symmetry of the operators AK, essential self-adjointness, to derive special properties of the spectrum. And that's where actually the quadratic operator tensors come in. That's where we'll discuss that in more detail. Now, what happens when the null space of T out of lambda depends on lambda? Then that approach is no longer feasible, and instead, one can't just take our Hilbert space F1. See that first arrow there. Then we have that operator polynomial L going from F1 to F1. One has to extend that F1 a little bit between F1 and F1 cross F2 to Hilbert space H, which essentially takes care of the lambda dependent boundary condition. For quadratic self-adjoint operator tensors, let MK8 be self-adjoint operators in the Hilbert space H, and consider the quadratic operator tensor L of lambda. Let us just look at some examples. Okay, so there's a general case. Sorry for that confusion. So we are looking in particular at isolated eigenvalues of finite multiplicity. So what does it mean? We have an isolated eigenvalue of finite multiplicity if lambda is isolated in the spectrum of T. The dimension of the null space of T of lambda is finite, and the supremum of mu of y, where y in H of lambda E, that supremum is less than infinity. Now, what does H of lambda E mean? These are vector functions from omega or from a neighborhood of lambda into the Banach space E, such that this is holomorphic, and mu of y would be the multiplicity of the zero of ty at lambda. What does it mean? T is holomorphic operator function. Y is a holomorphic vector function. So ty is a holomorphic vector function. And then it will have a zero because y 0, then we have this t of lambda x equals 0. So that means add lambda that is 0, so it has 0 of a certain multiplicity, and that is a mu of y. And in that case, y is called the root function of t at lambda. And now we want to give criteria for eigenvalues which are isolated. And we need the definition of the Fredholm operator. Most of you will know that. That's an operator, closed operator. There's a dimension of the null space, and the codimension of the range are finite. And now, then we call our operator function Fredholm value. Then t of lambda is Fredholm for all lambda and omega. And now we have the theorem by Goffberg and Segal, which goes back to 1971. If t is Fredholm value, then either the spectrum of t is all of omega, that's a non-interesting case, or the spectrum of t consists of isolated eigenvalues of finite multiplicity. So let's look at examples. Then we have a differential operator, an ordinary differential operator. And we consider the domain of the differential operator to be the Sobolev space Hn01. We have an nth order differential operator, and that's set of all functions which has derivatives up to order k, derivatives in the sense of distributions, such that these derivatives are again at L201. Then there is the Sobolev space. It's a Hilbert space, but it's the only thing we need right now is that the Banach space, the coefficient in that differential equation depend polynomial on lambda, and our operator goes into F, which is split into two parts, F1 and F2. F1 is the range of the range space of the differential operator, which is L201. F2 is the range of the boundary conditions, which can be written as TR of lambda y equals W0 of lambda y0 plus W1 of lambda y1. The capital Y is a vector consisting of the function y, its derivative up to n minus first derivative. For every boundary condition can be written in that way. And then our T is Fredholm operator value. So, and again, that's only a polynomial, but we have seen before that holomorphic operator functions occur naturally when we take inverses, but they also occur here in a different context. Namely, when we take for z of t and lambda, the one schematic of a holomorphic fundamental system of solutions of PD, then the function m of lambda, w0 of lambda, z0 of lambda plus w1 of lambda, z of 1 and lambda. It means we substitute the fundamental system into the boundary condition. Now, defines a holomorphic matrix function, and since it is operating the M of lambdas are n by n matrices, it operates in finite dimensional space. So it is indeed Fredholm value and clearly holomorphic, no more polynomial, and all the spectral properties of the operator function T are already contained in the matrix function M of lambda, for example, spectrum, spectra, coincide, eigenvalues, eigenvectors can be found from M or T and the other way around. And so now one aspect which occurs here, this such general operator terms is that we have associated them. That means when we take an eigenvalue of T and we consider now a root function, as I said before, and writes it as y of z equals some j from 0 to k, z minus lambda to the power j x to the xj. This just goes up to k. That's also a function. And then we look at any index m greater than 1, and xm is said to be an m's associate vector if that vector function Tf has a 0 of order at least m plus 1 and lambda. So when that function Tf has a 0 of order 2, for example, then there's a first associated function. And below, when we have actually m equals 0, then we just get the eigenvalue expansion if I include that. For m equals 1, then we have t dash of lambda x0 plus t of lambda x1 equals 0 as a condition for existence and determining associated functions and so on. So associated vectors only occur with non-self-adjoint operators, but we will see later that when we have self-adjoint pencils, they can also occur. And now we call such a set x0, x1 up to the chain of an eigenvector associated vector, and I've explained root functions before. And then it's another notation, namely canonical system of eigen and associated vectors. That is, we have a basis y01 to y08 of the null space of T of U, and then we have the corresponding multiplicity of x01 to x0r, and we require that these multiplicities are ordered, and 1 bar is greater than m, 2 bar, and so on, and they are maximal, so that m1 bar is the largest multiple, multiplicity, m2 bar is the largest multiplicity of all vectors, of all eigenvectors which are independent of x0 and so on and so on. And then this system is called the canonical system of eigen and associated vectors. And if we consider the corresponding root function, then we call that canonical system of root functions. Root functions are easier to deal with because they are shorter, more compact implementation. And right here. Now, we come to bi-orthogonal system. That is, you remember that for self-adjoint operators, eigenvectors are orthogonal. You can, eigenvectors to different eigenvalues are orthogonal, and you can also find the base in the same eigenspace, which are orthogonal. That no longer is true for arbitrary operator pencils, now, simply because they're working in different spaces. But we still have something else, namely by asymptoticity, and for that we just introduce the dual spaces and the adjoint operators. That is the usual definition. And then for each canonical system of root functions of the original operator, there's a canonical system of root functions of the adjoint operator from f dash to e dash, which satisfies the condition that d by dl, dl by d lambda to the power l, so the l's derivative of eta I dj is delta ij delta 0l. It looks quite complicated. In the eta I, we take the t yi. Remember, when we have a minus lambda identity, just that the ty is minus yi, and the eta I is then also multiplied by minus mu, that minus mu to the power minus m alpha. So, and then we get that by orthogonal relationship. It's just written down here in terms of root functions because it's much easier. In terms of eigenvectors and associate vectors, we get actually yeah, we have 3 parameters, I, J, and L, then we could get 5 parameters. And one important property is actually that if we take T inverse and subtract the sum J from 1 to n, that minus mu to the minus, which should be actually, okay, that mu should actually be a lambda here. Yj tensor dj. So we have the tensor product of the root function, the corresponding root functions multiplied with the corresponding that minus mu to the power minus that multiplicity of the corresponding root function. Then we get a holomorphic operator function. So that means these root functions have all the information about the principal parts of the inverse operator function. Okay, so now I'm back to what I already talked before. Now, okay, we can go to the quadratic self-adjoint operator pencils. Here we are going to consider an operator pencil of the form lambda squared m minus I lambda k minus 8. And now, this is just a formal pencil. So what is the domain? Now, we could take the domain of L equals the domain of M intersected with the domain of K intersected with the domain of A. That again, as I said before, may not be dense in H, and again, L of lambda may not be closed. Now, we will consider here a very particular case. Namely, that the operator M is greater than 0, the operator K is greater than 0, and both operators are bounded, and A has a compact result. And also, the null space of A intersected with the null space of K intersected with the null space of M is 0. That, okay, if that would be different from 0, then the resultant set would be empty. So that's an uninteresting case. Now, if we then put E equals the domain of A, this is graph length, and f equals 8, then L of lambda becomes a Fredholm operator tensor from E to F. And as I've already indicated before, the resultant set of L equals the resultant set of T. That means this T of lambda would be a bounded representation by bounded operator function. And so we already know that you can actually use all the properties we have found from the bounded operator function towards this tensor. But now, what particular problem or property might it actually have? Then, okay. So let us now take an eigenvalue lambda in C, and we write down the eigenvalue expression. Lambda squared minus lambda squared mx and so on. Then we take real and imaginary parts, and it's now simple calculation actually, which shows us that what I've shown here is that there can't be eigenvalues with real part different from 0 and imaginary part less than 0. And one can also show similarly from that if A is greater or equal to 0, then actually all eigenvalues lie in the upper half plane. So the bottom line here is eigenvalues lie in the closed upper half plane or possibly on the negative imaginary axis. And now let's look at associated vectors. So you know when you have A minus identity, A is self-adjoint, there are no associated vectors. Let's just take the case K to 0 just as a simple indication. Then similar calculations, similar simple calculations show that if lambda is different from 0, then we won't have associated vectors. But if you look at the second displayed line, x0 is an eigenvalue. And lambda equals 0. Then 2 lambda mx0 is 0. If you put x1 equals 0, then also x term is 0. So 0 would then always be an associated vector when we consider the eigenvalue lambda equals 0. Now, a reason behind that is if you write lambda squared equals mu, for example, then all the eigenvalues would be simple. There would be no associated vector. When we split non-zero mu, then we still get 2 where the eigenvalues cover everything. But if you look lambda squared doubles the eigenvalue, but there's no more eigenvector, so we must have an associated vector. That's somehow a heuristic reason behind it. And associated vectors, now in the general case, K equals 0, K different from 0. In case lambda equals 0, 1 is actually the maximum multiplicity of that eigenvalue. It's really not that important, but for lambda different from 0, we could actually have larger multiplicities. And now we have eigenvalues on the negative imaginary, possibly eigenvalues of the negative imaginary. But they are also particularly nice in that sense that they are all simple. That means there are no associates. And there's even another property of these eigenvalues. Eigenvalues on the negative imaginary axis, lambda minus k, let's say, are always or can always be paired with an eigenvalue lambda k on the positive imaginary axis, so that the imaginary part, of course, they are all imaginary, now the sum, the imaginary part of the sum is greater than equal to 0. So, in other words, for each eigenvalue on the negative imaginary axis there, you compare it with an eigenvalue on the positive imaginary axis, and that eigenvalue on the positive imaginary axis. It is at least as far away from 0 as the eigenvalue on the negative imaginary axis. And that there must be distinct with multiplicity. So, for example, if lambda minus k has multiplicity 2, then we can, or let's say lambda k has multiplicity 2, then that lambda k can occur twice. Now let's, okay, I still have about 5 minutes. So let's go for some examples. The regular problem. That is minus y double dash plus qy equals lambda squared. Y is a particular case of the S-wave radial Schrödinger equation. And Reggie assumes that the potential Q1 has a bounded support. So the Q1, which is plate formula at the bottom of the slide, is Q of x, when x in the interval 0a and 0 other one. And one is looking for solutions which are L2 on the positive real axis. And we have the bounded condition y of 0 equals 0. Now, then one looks at the Yost solution. Then the potential is 0. On that case, of course, we have the solutions e to the power minus I lambda x and e to the power I lambda x, and that would be the only one which e to the minus I lambda x, which would lead to a solution which is L2. So taking that solution and any of its multiplicity of its multiples, then evaluating that at A, we get y dash of A plus I lambda y of A equals 0. So that is what that your solution gives at A. So that gives us a boundary condition at A. So we have a boundary condition at 0 and the boundary condition at A. And you see that boundary condition depends on lambda. And that is now a holomorphic quadratic tensor operator, tensor, as we have discussed before. And now let's look at the setup. So here our Hilbert space, because we are here now with what we will see indicate later on this slide, self-adjoint operator, and we are looking at the Hilbert space, and here we have L2 0a plus c, c to the power 1, which comes from the 1 lambda dependent power. So that part is considered to be inhomogeneous here. And we have now 3 operators. The operator A is in the first component, the differential operator. In the second component, C is mapped into y dash of A. Of course, one must look y, C in conjunction. So it formally does not depend on C there, but that does not matter. The domain of A, that's now the set of all y and C. The y of 0 equals 0 and C equals y of A. So we have here the normal 2-point boundary condition, and that gives us self-adjoint operator. Well known. These operators are self-adjoint. The operator M is just I0, 0, 0. So that we get the lambda squared is the differential part, and the k is 0, 0, 1. That's where we have, okay. You see, we have the lambda here in the differential part, that's the k, I lambda, and where in 1, we have the lambda squared in the differential equation, and here we have the lambda, linear lambda, in the boundary condition. That's where the setup comes from. And then we have all our assumptions satisfied, in particular A as a conflict resolvent, both M and A are greater or equal to 0 and M plus K is the identity. And our next example is very similar. That is a fourth order differential operator, but again, quadratic dependence on the eigenvalue parameter on the right. We have 4 differential equations, and you see here one of the differential, one of 4 boundary conditions, and one of the boundary conditions depends on lambda. And so this is a problem of small transversal vibration of an elastic beam compressed or stretched by this force proportional to function g of x, and the boundary conditions are hinge boundary conditions, and at the right endpoint A we have viscous friction. That's where the eigenvalue parameter lambda comes in. And also in this case, we have a very similar setup of these operators. And okay, I just wanted to indicate, and I can't really go into details here, that we can now use asymptotics of eigenvalues, and there actually the second part comes in. So far it was mainly operators here, but if one wants to calculate the eigenvalue, a lot of complex analysis comes in. Rouché's theorem, for example, one has first a very rough approximation of the eigenvalues, and then one refines them and so on. So, but that was just an introduction of a quite large field, and I haven't written down here any references, but if you are interested, there's one book with Manniken from 2003 on non-self-adjoint operator functions, and one book from 2015 with Quadratic on, in particular, the self-adjoint, and these 2 examples are actually also in that book. And there you can, of course, see all the other references. If you don't have that book available, I just looked it up. At least the references are visible to non-paying customers. Okay, thank you very much for your attention.
Hi, yeah, that was a great talk. And I just want to find out the motivation for the choice of a self-adjoint. If the ultimate motivation is applications, applications come from operators that are also non-self-adjoint. Is there any special reason? Is it because of difficulties with respect to so-called denseness and other things, or what other motivation could have made you?
Okay. The motivation for the self-adjointment, and I actually explained that in particular this example. No, I didn't really explain that this example, but it comes in the example. When we have self-adjoint quadratic operator, for example, then we see that the eigenvalue distribution is very particular. In the lower half plane, in the lower open half plane, we can only have, for that particular type of operator pencils, eigenvalues on the negative imaginary axis. And they're also governed by the number of the eigenvalues of the operator A in that field. So that is only a quite large restriction. We don't have any more real. So that's clear. So it's no longer as disjunct a single self-adjoint operator, but we still have quite a restriction of the location of the eigenvalues, and that in turn can have impact on stability of the solution. And we know that the eigenvalues only lie in a certain part of the complex limit. I hope that answered your question somehow.
Oh, yes, thank you. Thanks.
Thank you, Justin.